We have already seen the introduction part of the graphical representation of motion. Now, let's understand how distance-time graphs help. So, let's talk about distance-time graphs. See, these graphs, they are used to represent the change in position of an object with respect to time. That's why they are distance-time graphs. So, distance-time graphs, that are dt graphs, they are used to represent the change in position of an object with respect to time. In this graph, time being the independent quantity is taken on x-axis and distance being the dependent quantity is taken on y-axis. dt graphs plotted under various conditions, and they can give us some information. Distance-time graph, they help us to find out type of motion made by the object. In that, if the object is stationary, is it in uniform motion or non-uniform motion? Or if the object is in uniform accelerated motion. The second thing dt graphs help us to find out is to estimate the position of a moving object. And the third thing is to determine the speed of a moving object if that object is performing uniform motion. Let's first understand how type of motion can be identified by dt graphs. What happens and what kind of graph we get when an object is at rest? Look at this graph. Here, the time is on x-axis and distance is on y-axis. Now, as you can see here, at 2 seconds, the object is at 6 meters. So, this point represents 2 seconds and 6 meter distance. This point represents that when it is 4 seconds, the object is at 6 meters again. And at 6 seconds also, the object is at 6 meters. Similarly, at 8 seconds and 10 seconds also. Here, we can say that the time is changing from 0 to 2, 2 to 4, 4 to 6, and so on. But the object is not moving. It is still at 6 meters. Now, when we join these points, the line we get will be parallel to the x-axis. This is your x-axis, and this line we get is parallel to the x-axis. So, we can say that the object is stationary. Look at this line. Even the time is changing, but this object is not changing. So, we can say that when the object is stationary, the line showing the motion will be parallel to x-axis. And this is how this kind of graph can tell us whether the object is stationary or not. So, this is about the object when it is stationary, means not moving. Now, let's talk about when the object is in uniform motion. Look at this graph. In this graph, you can see here that at 2 seconds, the object is here at 2 meters. At 4 seconds, the object is at 4 meters. And if you take this 6 seconds and if you go here on the y-axis, you can see the object is at 6 meter. So here we can say that at every 2 seconds the object is moving 2 meter. Look at this. This distance is 2 seconds and this distance is 2 meter. Again, from 2 to 4 it is 2 seconds, and again from 2 to 4 this distance is again 2 meter. Now we know that if the object travels equal distance in equal interval of time, the object is said to be performing uniform motion. So this is a clear case of uniform motion. And this line showing uniform motion will be a straight line. But remember, it is not parallel to x-axis. In fact, it's going upward. So, in uniform motion, the distance traveled by the object is directly proportional to the time taken. Second thing, we can say that this type of graph shows that the distance is increasing at a uniform speed, at a uniform rate. Note that if we would have used displacement in place of distance, this would have been uniform velocity. So it would have been uniform velocity time graph. Now let's consider the other condition, when the object is in non-uniform motion. Look at this graph. Here in this graph, scale on x-axis is 2 unit is equal to 15 seconds. See this, from 0 to 15, 2 units are used. From 15 to 30, again 2 units are used. And on y-axis, 2 units is equal to 1 meter, showing distance. And here, when the time is 15 seconds, the object is at 1 meter. When it is 30 seconds, the object is at 1.5 meter, because this point is between 1 and 2. When the time is 45 seconds, this object is at 3 meter. Similarly, at 60, the object is at 4 meter distance, and at 75, it's again going at 4 meter distance. Sorry, at 60 it is 2 meter, and at 75 it is 4 meter. So now we know that if the object travels unequal distances, look at this. This is, all these points are representing this distance between them. It is representing that the distance is unequal. So if the object travels unequal distances in equal interval of time, then it is said to be performing non-uniform motion. So here this object is performing non-uniform motion, because the graph is, the distance is not equal. See this, from this point to this point, this is the gap, and from this point to this point, the graph, this gap is more than this. So this is a clear case of non-uniform motion. Now, what happens when the object is in uniform accelerated motion? What kind of graph we get? See, here at 10 seconds, the object is at 5 meter. See this, between 0 to 10, this point is 5, because it is half. So naturally, at 10 seconds, the object is at 5 meter. At about 22 seconds, the object is at 15 meter. And at about 32 seconds, the object has covered 30 meter distance. Now, by joining these points, we get a parabolic curve. And this shows that an object is making uniform accelerated motion. Remember, the graph showing straight line is of uniform motion, and this graph is showing uniform accelerated motion. So this is the difference between uniform motion graph and uniform accelerated motion graph. This is how we have seen that how graphs help us to study the type of motion made by the body. That is, whether the body is stationary, whether the body is performing uniform motion or non-uniform motion or uniform accelerated motion. In our next video, we will try to find out how graphs help us to estimate the position of a moving body and how it helps us to determine the speed of a body performing uniform motion.